So I'm going to go ahead and get started with the schematic capture tool. This is called OrCAD X Capture, and it's also known as Capture CIS if you've used OrCAD before in the past. So when you first launch the program, you're greeted with the start page. This can be turned off. That's come up before. It doesn't have to always launch this start page if you don't want to. It might be useful to go over when you first install the tool. So here to the left, if I want to open up the user guide, I can easily access it. Selecting documentation, it's going to open up a separate window. Depending on what I'm looking for, I could scroll to a specific topic and search the user guide directly from the schematic capture tool. There's also how-to videos. So depending on whether you're working in the schematic layout or library authoring, you can look at all the available videos, and selecting any one of them, it will launch YouTube and go over the specific topic. So in addition to these videos, there's also a useful PSpice guide embedded in the software. You could access it from here, and this is not limited to just PSpice. Depending on what the topic is, it'll walk you through the theory of it and what it's doing, and then how to implement it into PSpice. So everything in this guide is very useful, very well written, and I sometimes catch myself coming back to here and getting flashbacks from college days. So the first thing I needed to do was create a clock signal. And so I did that using a 555 timer. It can be configured as an oscillator, and what it does is there's two comparators, and it's reading the input voltage and then 2/3 and 1/3 of the input voltage. In my case, it's going to be 5 volts or 9 volts. One of the reasons why I chose a 555 timer is because it has a wide operating voltage. So depending on the input, I know it's going to output the clock signal that I'm looking for. And so depending on the two voltages that it's reading between threshold and trigger, it's fed into these comparators, and it'll either turn the output on or off. So the 555 timer can be wired a couple of ways. There's astable and monostable mode. So this is currently set to astable mode, which means there's no stable state. So it's always switching between a high and a low output. And so in the data sheet, there are a couple of equations that are available, and you can calculate the frequency and then the amount of time that it's low and the amount of time that it's high. There's multiple ways to get this symbol into capture. So the first way, you can check the PSpice library that's included with the software. Depending on what you're looking for, there's a large list of components to choose from. There is actually a 555 timer available. The other thing you can do, and this is what I did in real life, is you can download and bring in an external .lib file. So you can just go to the simulation profile, and in configuration files, I added it as a global library, but you can bring the actual .lib from another provider like Texas Instruments. And so depending on these values, the voltage is going to charge this capacitor up to 2/3 the nominal voltage and then down to 1/3 the nominal voltage. Depending on that value, it's going to switch the output from on to off. So for my digital clock, I want this output to be a 1 Hz square wave. I want it to turn on and off at a certain voltage forever. I just need it to stay consistent. And so I currently have it for 5 volt input. And so it will switch on and off between 0 volts and 5 volts with a 1 second period. Calculated these values beforehand, and so now we can go ahead and run the simulation. I currently have it set for 10 seconds, and so it'll read all my PSpice enabled parts, and then up top I have all my commands for PSpice. I'll go ahead and place a voltage probe on the output. And then if I bring the simulation window over, you can see my output. I could turn on the cursor, and I did the calculation before, but it should be close to a 1 second period with a 50% duty cycle. So I can take this a step further and use what's called the advanced analysis. So PSpice includes something that's called Optimizer. And what I can do is I can select any number of components that are in my circuit. And in advanced analysis, I could export my current parameters that I calculated before to the optimizer. So here I have 4 values that I set. I'm going to get rid of this initial condition. And what I really want to do is I want to sweep the original value across a min and a max range. So I'm going to change this max value to 2 meg. And I'll change this to 400K. And I'll leave that. So once I have the components that I want to test and the min and max sweeping values, we got to add a measurement. So my 2 important measurements for this case is my period and duty cycle. So my duty cycle, I'll go ahead and choose this one. I'm sweeping over a set x-axis from 2 to 8 seconds. And I got it as close as possible to a 50% duty cycle. I don't need it to be at 50%. It can be slightly below or slightly above. What I really want is the period to be as close as possible to 1 second. So duty cycle, I'll go ahead and give it a min value of 0.48, max value of 0.51, and then the period. For this, I want it to be as close to 1 as possible. And then there's the wait entry. This is the priority that you want to give the specific measurement. So if you want to assign a higher priority, you would assign a higher wait. And then lastly, we select the engine that we want to run. There's modified LSQ, least squares quadratic. I had to look that up. And what that engine will do is it'll do its best to rapidly converge on the goals that are set here. There's a random engine, which will choose random values between your min and max values set for the components. And then there's discrete, which will choose commercially available component values. You'll notice that the optimizer will actually calculate the best possible value to meet the goal. Discrete will choose orderable values. So this will replace my current values, or my original values, with slightly modified values and rerun the circuit simulation over and over up until it reaches the goals or constraints that I've defined. So I currently have 2 goals set, and we will let this run a couple times and see what the optimizer returns. So the first simulation finished, and the first set of runs modified my R2 and C3 value only. So I'm going to go ahead and change these min and max values to the actual value that I want it to be at. And I'll also go ahead and change the weight for the frequency to something higher and see what the next simulation does. Now, if we look at the graph, you can see my values have changed quite a bit. So R2, C3, and R1 are all very different than my original value. And my frequency is close to where I want it to be. We're looking at a 122 milli% error. I'm not designing the next atomic clock, so I'm happy with these results. So I can continue to run this if I'd like, probably get this closer to 0% error. But I did already buy the resistors and capacitors for the values that I calculated. So I'm going to go ahead and get out of here and continue on. So here's my clock output that I know that it is going to work without having to connect it to a breadboard or an oscilloscope. So this will be fed into the rest of my circuit. And for the rest of the simulation that I did with the counters, I added a digital stimulus for my clock. I came into the editor and set the values that will be coming out of the 555 timer. This will all be digital readings in PSpice now. Realistically, this will be a 5-volt output. So before we get back into Capture, I want to quickly go over the rest of my design and the other components that are in it. So coming out of the 555 is a 1-second pulse, and that is being inputted into my CD4510B clock signal. And what this component is doing is it's a binary coded decimal, BCD for short, counter that is counting from 0 to 9 and then resetting. So depending on what moment of time I'm in, this binary value is outputted into the input of my 74LS47 component. And this chip is doing two things. The first thing is it is decoding this binary value to its respective decimal value. And then the second thing is it is driving my 7-segment display, my last component here on the bottom right. And it's either turning the voltage on or syncing the current to turn one of these segments on. And so for the rest of my PSpice simulations, I was validating the outputs of all my CD4510s that I had for my seconds, minutes, and hours. And so starting with the seconds, I was making sure that this component would take my 1-second pulse coming from my timer and be able to store its decimal value starting at 0 all the way up to 9 and then resetting. And so depending on what my pulse is and what moment of time I'm in, all of these gates are outputting a specific value. And so for my minute circuit and for my second circuit, I used a couple of AND gates that were connected to my CD4510. And I'll show you that in a little bit. But what I wanted to do was reset some of the CD4510s back to 0 once the value hits 6 for 60 seconds and 60 minutes. So back in Capture, I have all the components I was talking about, nearly all connected together. I had to leave out my 7-segment display for this test because this isn't a PSpice enabled part. I still was able to see the behavior coming out of my 741S47 by just connecting voltage pins to the ends of my current limiting resistors and validating the output that way. What I really wanted to make sure is, were my counters keeping track of the time correctly? And so for this test, here to the right, U12 is my 0 through 9 counter and should be counting from 0 to 9 seconds. And at 10 seconds, this should be set to 1. And U11 should be counting from 1 to 6 and then resetting with how I have my AND gate connected to it. And then this seconds circuit is fed into my minutes, and then similar for my hours. I'm not going to go into the inner workings and detail of circuitry that I have for my clock, but you will have access to this data set after the webinar for you to look deeper if you would like. And so I have voltage probes connected to U11 and U12 for seconds, and PSpice is capable of simulating digital outputs. My simulation settings are nearly the same. I increased my time a little bit to past 60 seconds to make sure this whole circuit behind me does reset, and it's still a time domain analysis. And so hit OK, and if I run this simulation, you could see slightly different measurement. These are now digital readings, either true or false, 1 or 0. And activating my cursor, I could read the values of U11 and U12. So keep in mind, U11 is my 10th digit and U12 is 0 through 9. And so right at 10 seconds, my least significant bit of U11, my 10th digit, should be 1, and it is. Everything else is 0, and U12 should be 0 as well. We're at 10 seconds. And so I did this for seconds and hours and minutes, and I could view my output was showing the correct value. So at 15 seconds, U12 Q3, that is 2 squared, and Q1, 2 to the 0, that's 1, is reading 5. And then moving on to 60 seconds, everything should be back at 0, and it is. So I know my counters are working correctly, and I also know that my displays will work correctly from analyzing the binary output from my counters. So before I move on to the layout and the rest of the webinar, there's a few more things in Capture that I think are worth noting. And so I have a duplicate design that I opened with everything connected. And I also added a couple switches to set the minutes and the hours, as well as a couple connectors for VN. Realistically, I'll end up choosing one connector. I just wanted to validate a barrel jack connector footprint that I have. But you might be wondering, how do I get these components into my design? How do I choose a symbol? And how do I choose a footprint? And OrCAD X has a newly designed component explorer. I slightly showed it earlier with the PSpice components that are available, but you also have access to third-party content providers for symbols, footprints, and 3D models. So depending on what you're looking for, you could search for an actual part number and either download it, or what I've been starting to do, adding it to my workspace, your library. And this is a extremely easy to use tool to attach all the different building blocks that make up a component, a symbol, footprint, and a simulation model. And so looking at my 555 timer, for example, I can attach a symbol, a footprint, and even a PSpice model if I wanted to, all in one location and ready to go for the next design that I'm working with. And so I just wanted to show this for a second. You could attach a primary footprint, an alternate footprint, and for my example here, a PSpice model. You could also attach the manufacturer part number, and there's also life cycle information that can be applied to it. The other thing about these workspaces is I can share them. And so when it's time to have a central library where everyone is using the same part, I can go ahead and create custom workspaces or just share my own personal one. And I could add users to either custom workspaces and have a central database for libraries and also projects. So if I wanted to, I could publish this. And let's say I'm starting to add it to our own internal library. I could give it a revision, a comment. I can lock it, unlock it to avoid unwanted modifications, and then publish it for what might be a central library shared across my team. The thing I had to do was order all of these parts. And so Capture CIS, you're more than capable of outputting an Excel file and attaching part numbers to it and sending that away. There's what's called LiveBomb now in OrCAD X Capture. And what this does is it will grab all of the parts in my design and create a ready-to-go bill of materials that I could attach supply chain details to. I could sort by unique parts here, and selecting any one of my components, I've matched a lot of these already. It'll show me alternatives as well as all the information possible for the particular part that I selected. It looks like I have one left. I did this on purpose if you couldn't tell already. But to add a part, I search for the part number that I want, and selecting one, it'll put its properties here to the right. It'll show me the number of distributors that have it, the pricing for it, and the lead time, the important things. And I can go ahead and hit the plus button and add it for my U5 component. So this is another way to generate a bill of materials with a lot more information for availability and pricing. If I want to, I could also modify these columns and what gets included or excluded. So depending on the data field that I want to include or not include, I can make modifications to that here. So I'm going to go ahead and move on to the layout side of the design. So Cadence recently released a brand new layout editor tool called Presto. And so that's what I'm going to be showing today. There is still the classic Allegro PCB editor tool available. And so when you do create a new layout, you have the option to select which editor you want to use. And so once you select the editor that you'll sync the design with, we can go ahead and create a new PCB. And here you have the option to select an input board file. So if you have a standard board size that you always use and a stack up that may always be the same, you could create a template and reuse that board file for another design. But let's say I'm going to create a new board. I'll show you what the new board looks like. And starting the new board, it'll ask for the license. And once this finishes loading, it'll open up a blank board outline, 6 inches by 6 inches, and also two conductor keep-in and component keep-in layers. You can disable these if you want, or you could also set the value that'll be the distance from the board outline. So I'll go ahead and zoom out a little bit. And so the first thing I did was set my units. Here to the right in the Properties tab, you could switch between mils, millimeters, micrometers, centimeters, or inches. You can set the accuracy and the sheet size of the drawing area. And then here to the left, I have my visibility panel. And so you could turn on or off some of these layers that are shown here, like my masks. Maybe I don't want to see that right away. And then top and bottom layer, as well as all of the other layers that can be turned on or off. Once I do configure this, I can save these views. So I'll show you in a little bit. I have different views that I just turn on or off. And if I have a new one that I want to add, I could add it here. So one thing that changed for me was this board outline. And there are a few ways to create a board outline. The first is I can just click and drag and make the board outline bigger or smaller. Or I could also use the available tools in Presto, draw design outline, and I have the option to draw a rectangle, polygon, or circle. Presto also supports IDX and DXF. If you have a board outline in one of those formats and you want to use it, that can be imported. But we also have MCAD X now, and this is a direct integration into SolidWorks. And so in our next webinar, we will be showcasing this, how to use MCAD X and how it integrates with SolidWorks. So this is another useful tool that comes with OrCAD X and can be used for the board outline and also component placement. So large components, you will see in future webinars how communication is handled between SolidWorks and OrCAD X. So if I wanted to, before my mechanical team makes the decision on what this board will look like, I can go ahead and start with a circle. Why not? So here I could also pick the origin location. That would be useful. And then my stack up. So I got to set the stack up, and that's done with the cross-section editor. And so opening up this, by default, it'll start off with the top, bottom layer and a dielectric layer. And here I could add a new conductive layer if I want. If I'm adding a multi-layer board, I would do that here, and I would come to add layers. And if I do choose below, conductor will activate. But if I want a layer above, I can go ahead and choose what mask I want. So I want my solder mask, choose its function, and then the material that you want to use. As you can see, there's a huge list of material to choose from. But once I find the one I'm looking for, I just select Add. So I'll go ahead and do this for the rest of my layers, and this will be a 2-layer board. things worth noting for this webinar is the material that I used for my top and bottom layer. You could actually choose 1 ounce copper. It should then update a bit. Thickness. And it doesn't really apply for this board since it's 2 layers. But if we look in the signal integrity section, there is an area where you could set the target impedance that you want, and it will adjust the required width in order to meet that impedance. So for a multi-layer board, this would be useful, or when impedance matters for like an antenna or a differential pair, setting this can help with what trace width is required. And so I'm going to go ahead and undo this, set it back to the default. I can here to set up my constraints. So Presto comes with a new constraint panel, and depending on the constraints that you need to set, the basic ones can be visually seen here and set here as well. So for my trace width, I could set my minimum width that I want to allow, my neck width, as well as my spacing constraints. So from line to line, to pad, pad to shape, everything can be set on the constraint panel or in my constraint manager. And so the constraint manager is the same set of rules. There are more that can be applied in here. It also gives me the ability to assign rules to specific nets. So if I select anything underneath the net folder, bring up all of my nets in my project. And this is another way to assign rules to either everything or to individual nets. So with this clock being a 2-layer board, I needed to make a physical constraint for my trace width, specifically for my voltage pins. And so to create a new rule, I can come to the physical tab and select all layers. And you have the default value, which is what the panel is reading. If I want to create a new rule and assign it to specific traces, I select my design, create a new C set, and give it a name. And there are calculators online, and it can give you a rough estimate of the required trace width based on the copper thickness and the current. I know that I'm not going to have more than 1 amp of current passing through this board, so I decided 30 mils for my voltage traces will be thick enough. So once I give it a name, I have to change the value. And so here I would change this from 5 to 30. Can give it a absolute value, or I could leave it blank. My minimum value is what's important and what the routing tool will look at when I set this. And then I have to go to the net. And so right now everything is set to default. To find my voltage traces, I have them labeled VN. And here I would change from default to the rule that I created. And so I did this for VN and then also my signal traces. And then I also matched my spacing constraints to the capability of the manufacturer that I used for the boards, which was OshPark. And so I'm going to open up the completed design in a minute, and once again you'll have access to the data set with a completed design. But now if I route any component with this trace involved, it'll route accordingly to 30 mils. And so everything else is currently at 5. So I can get out of here and I'm gonna move this a little bit. And so most of my commands are here to the left. Right-clicking will expand the command menu. And to place a part, there's 2 ways, series or cluster. Series will place one part at a time. Cluster will place multiple at a time. So if I multi-select one or more than one with series, it'll ask me to place one at a time, and then cluster multiple at a time. And then I can go back to the move command and start to place these where they're going to go. If I route, this will be a 5-volt trace. Looking at the options, there's manual and assisted mode. Auto, it'll use the constraint value that's given. And so if I start the trace, it'll be 5 mils. And then same for VN. You can see it is now 30 mils. Then if I turn on assisted, it'll do its best to not overlap any pins. If I turn it back to manual, you'll get a DRC. So I'm gonna switch gears to the completed design now and show manufacturing files and then end with the live footage that I got for building this clock. So I think I mentioned it before, but we're going to have a separate webinar that goes into detail with the MCAD integration. And so the capability is there, it's included with the software, and all it really needs to be done in Presto for the translation to work properly is defining the stack up, the number of layers that are going to be on the PCB, getting the thickness down, and then placing the critical components. So behind the scenes, I went to each of these components, specifically the footprint, and in order for MCADX to work, a step file must be mapped to the footprint. And so looking at the 3D view of the 7-segment display, for example, I just choose a step file from my file system, map it to the footprint geometry of the pads, and then save it. And then once you do this step, you are done. So you are looking at the board that I got manufactured. I did the assembly in-house, and I am running out of time, so I do have live footage I want to show you of me assembling the board and some of the roadblocks I hit along the way. But all my traces are routed. Put a copper area for ground on the bottom layer. I'm going to show you the manufacturing file output and generating the manufacturing files. So OrCAD X Presto has what's called Live Dock, and I already have one started here. But if I open it, this is a new tool that lets you place fabrication artwork, assembly drawings, stack ups, anything relating to the layout in a ready-to-go drawing that can be exported. You can put all your variables here to the right. And I started to separate the drawings. So there's fabrication top, fabrication bottom. And if I want to create a new drawing, just hit the new drawing button. And if I want to add drill drawings, for example, I can just select the drawing that I want, place it. Drill chart will prompt me to choose an area. And then I can modify the drawing and make it look exactly how I want to. And so depending on the requirements, there's the export to manufacturing part, which is generating the Gerber files or the ODB++ files to send to the fab house. And so when you're in here, it's turning on or off the output that you want, and then configuring the settings for it. So once you have enabled or disabled the files you want to include, I just export it. And then this gets put into a specific folder. And so from here, I'm ready to send these drawings to Osh Park. I get a view log of everything, and it all gets placed in a zip file that's ready to be sent to the board fabricator. So now it's time to switch gears to the live footage section of building this board in real life. So I hope you enjoy the recording, and here you go. All right, so now is the moment of truth. We have soldered the board. Actually, forgot one capacitor, so let me do that really quick. All right, clear the area. Okay, so test one, everything is soldered. I currently have 5 volts set on the power supply, 700 milliamps of current I'm allowing, and my heart is racing. So now it's the moment of truth. Let's see. So yesterday I turned it on, and as you could tell, it did not work. So today's a new day, and I looked at the board, and it turns out U4, my LED driver, was connected backwards. So hopefully this was the only issue. Mistakes happen. And so I'm gonna flip the chip, and hopefully the board will work. So that took way longer than planned to desolder that chip, but it is fixed. It's on the correct way. And now we are ready for the final test. Fingers crossed, this will work. Okay, so I have a 2 amp current limit. Hopefully it'll be lower since I was burning that chip previously. All right, let's just go for it. Okay, so better sign. Our hours is currently at 1. Okay, we're almost there. So my hours is for some reason not resetting and my switch is not functioning. Alright, so little change of scenery here. I ended up redoing the board. My soldering skills could definitely use some improvement. And that last board, there was just too much room for error. My soldering was sloppy, and so I spent some time learning how to solder again and made a much better, prettier looking board that I'll show in a little bit. One test that I did, I already turned this on and it didn't work again. Turns out flux is conductive, and so I was getting a short circuit. My current was blasting through the roof. Luckily, I have current protection set on my power supply, and it also has short circuit protection. So the moment that I plug this in with power turned off, it'll beep at me if it senses a short circuit, and it was. So did some cleaning with some of these alcohol wipes, and this board looks beautiful. So now I have the current limited at 250 milliamps. I'm suspecting it'll need a little more power, and my voltage is set to 5 volts. And so this final test is going, well, I should stop saying final. This next test is seeing if the board will turn on and operate correctly. I've tested 0 short circuits are happening, every power and ground, used a multimeter, did the continuity test. It's looking good. So here we go. All my displays are working. That's a start. So U4, made sure, triple check that that was on the correct way. And right now we are at around 4.3 volts. So I'm going to go ahead and raise the current up a little bit, going 50 milliamp increments. So at around 320 milliamps, we're now at a constant voltage. So go ahead and zoom in. And it is ticking. It's at 1 second increment, thanks to PSpice. So now I'll go ahead and test the switches. So one of 2 things could have been going on with my switches. The first is both of them are connected to the output of my AND gate, and I found out the AND gate latches the voltage at either 0 or 5 volts. The other thing that could have happened is I had a voltage divider going on with my output of my switch. So behind the board there are some dangling wires that I soldered on to make the switches work, but it is now fully functioning. I can go ahead and set the time. Let's pretend it's 4:15, and I'll show you a close-up.